Sairam. Having seen the physical properties of aldehydes, ketones and carboxylic acids, in this segment we are going to study about various reactions undertaken by carbonyl compounds, where specially we will study about the aldehydes and ketones. Carboxylic acid probably will take it up at a later stage. So, how do these reactions of aldehydes, ketones happen? The first thing we have to study is what are its mechanism to undertake reactions, and then we can study various types of reactions and various named reactions. So, let us start first with the different types of reactions that are possible in these cases, where all these compounds tend to undergo nucleophilic addition reaction. Now, the question is, what is nucleophilic addition reaction? So, nucleophilic addition indicates that a nucleophile will come and attach on the carbonyl group which is there. So, in this attachment on carbonyl group which is there, a nucleophile indicates a compound which is present with large electron content. But if a large electron content comes, this will be a problem where in these cases the carbon group which is there will be present as an electropositive system, and this is present as electronegative system, which we know very well. So, in these cases, suppose if a nucleophile comes and attacks. Now, what do you mean by nucleophile? It is electron rich. So, where it should go and attack now? Definitely this is hydrogen, carbon and R is again a carbon system. These two people have almost same electronegativities, we have kept seeing that. So, the person who is running short of electrons is this carbonyl carbon. So, quite guaranteed that this nucleophile which is there will come and attack this carbon. So, what about suppose if there is an electrophile which is attacking? Suppose if we have an electrophile, because for example, what happens in this cases is generally we may tend to react with say HCl. Now, what will happen to HCl? It will split up as H plus and Cl minus. So, the question is going to be, where will Cl minus go and attack? Where will H plus go and attack? Pretty simple. This is negative. So, it should go and attack to the positive part, which we can call it as a nucleophilic attack. The positive part should go and attack to the negative part, which we call it as the electrophilic attack. So, here it is mainly first place the nucleophile which comes and attacks, and then the counter ion which is there can help and go and attack the oxygen which is there. So, if you see the system of the attack of the electrophilic systems which are there, we see in the diagrammatic view where nucleophile which is electron rich in nature will come and attack the carbonyl carbon. The carbonyl carbon is present in sp2 state, the reason being it has a double bond. So, when the nucleophile comes and attacks to the carbonyl carbon, the hydrogen or any counter ion which is there along with the nucleophile will go and attack the oxygen. That is where they tell that the net result is addition of nucleophile and H plus. Here they have considered that along with nucleophile H plus could be present across the carbon oxygen double bond as shown. So, in the steps you are able to see that nucleophile attacks the carbonyl carbon, hydrogen attaches the oxygen atom which is present. So, under this mechanism we now study a reactivity series for these compounds, because since we study both aldehydes and ketones simultaneously, the question now is, will aldehyde be stronger reactive or ketones? They say that aldehydes are generally more reactive than ketones in nucleophilic addition reactions due to steric and electronic reasons. So, first let us see what are these reasons as such. For example, let me take for my comparative study propanal and propanone. So, when I take these two compounds now, the question that is being sought here is that if a nucleophile comes and attacks, suppose this nucleophile attacks here also, it attacks here also. The question is, will this be a more reactive reaction or will the reactive reaction be the ketone one? Now, they seem to say, which we happen to read just now, that aldehydes are more reactive than ketones. And what is the reason for it? Nucleophile is somebody who has excess of electrons. So, this excess of electron system will come and attack. The moment it comes and attacks, there are two reasons now. One, they call it as steric hindrance, steric, which means size. Hindrance indicates something which is blocking. In this case, bigger groups which are present here, suppose if the nucleophile wants to come and attack from this side. So, the same arrow mark, let me show it like this. If it wants to come and attack like this, it will not be possible because big group is present here. This big group will give a steric effect where it will not allow this nucleophile to come and attack easily. But the same thing, suppose if the nucleophile wishes to come and attack from this side, then it is possible because there is a small hydrogen group which is present. We know hydrogen atomic number is just 1, which means that the atom is pretty small. So, because of its small nature, there is sufficient area for the nucleophile to come and attack. This is what is called as steric hindrance. Then what is the problem with ketone? This carbonyl carbon which is having delta plus and delta minus, nucleophile when it attacks here, here also it has one little big group. If you see with respect to hydrogen, it is pretty big only. If it wants to come and attack here, here also there is an alkyl group. So, in ketones, be very clear that the ketone general formula is RO R dash. So, naturally it means that on either sides there will be large alkyl groups which is present. But we know that aldehyde general formula is RCHO, where one side it may be big, but the other side is always the small one. So, which means that it is easy for nucleophile to come and attack. If this is steric reason, the other reason they call it as electronic reason. What is electronic reason here? We know that all these are electron donating groups. This is delta positive, this is delta negative. So, delta positive means it is running short of electrons, it is deficient of electrons. So, when it is deficient of electrons, there are people from one side, they may be a little big, but people from one side, the carbon atoms here can donate electrons. How do they donate electrons? Inductively. This has been studied in first year. So, inductive effect is seen from one side in this case. Now, what happens here is, since these are electron donating groups, the electrophilicity of the system will reduce a little, and a nucleophile would rather like to attract the most electrophilic carbon. If that is the case there, here on both the sides there are electron donating groups which are present. So, what are these both atoms or the groups doing here is, they are supplying electrons to the carbonyl carbon, thereby reducing their electrophilicity. What do you mean by reducing electrophilicity? Electrophile means electron deficient. But here, because of presence of these two, the content of electron is increasing, and therefore, a nucleophile would not like to attack here much strongly, because nucleophile is electron rich. It prefers a much more deficient electrophile which is there. So, among these two, which is a better electrophile? This is a better electrophile. Reason for that is, this is comparatively electron more deficient because electron donating groups are there only on one side. This is comparatively a little electron deficient, which means that it has more electrons because two groups are present on either sides and they donate electrons. So, what is this? That let us see in the explanatory part here, where sterically the presence of two relatively large substituents. What do we mean by relatively large substituents? It means that larger groups are present in those cases, and those large groups in ketones, it will hinder the approach of a nucleophile. Whereas in aldehyde, the large group is present only on one side, and therefore the hydrogen on other side can easily get you react. Electronically, aldehydes are more reactive than ketones because two alkyl groups reduce the electrophilicity of carbonyl group which is there. This is because on both the sides there are presence of the electron donating groups which is present. So, now we understand very well that aldehydes are preferably more reactive than ketones, and slowly now we will start to take up various examples of reactions which is there. The very first reaction is going to be the study of reaction of aldehydes and ketones with hydrogen cyanide, where this we study with the mechanism for this. So, what is happening here basically is that this HCN compound which is there is considered under basic medium, and that basic medium is denoted by OH minus which is present. So, in this OH minus compound which is there, we know very well that whenever we take a catalyst, the catalyst should come out as it is. So, in the first step what happens here is, though the reaction is basically the carbonyl group and HCN, this is what is the reaction, OH minus is the medium which is considered. We generally know that for all the mechanisms, almost all mechanisms that we at least study at this place, the first reaction or the first step is going to be the utilization of the solvent or catalyst, anything that we take, with the attacking reagent which is present. So, what happens here is HCN will react with OH minus, this is the first step, where this will give you Cn minus nucleophile and water. The hydrogen from this went and formed water. In the next place now, suppose if this group is considered, now please remember that if I leave it like this, it means it is a carbon. You must have remembered in the bond line formulas, if we leave it like this, it means there is a presence of carbon with CH3. But here for our understanding, we believe that because we are actually studying two groups here, aldehydes as well as ketones. So, let me take it for my study as R and R dash, where let me consider that R dash also may be H, because I want to talk even about aldehydes. So, in this case what happens, this is nucleophile. We now know very well that nucleophiles attack carbon because there is an electronegativity difference where this is delta minus, this is delta plus. So, the negative charge will definitely attack the positive part. So, what is left over here, R and R dash, let me write it as it is. Here Cn will come and attack, and because Cn attacks, already 3 bonds are there. So, can it form a C double bond O? It is not possible. So, the double bond will go on oxygen and therefore, it will hold a negative charge. Where did this negative charge come from? The double bond, the pi bond which was here was broken and both the electrons went and settled on oxygen. So, how do you stabilize this part? Because remember that you had water here, and when you use this as a catalyst or a solvent, it has to come back as it is. So, from this part, from this water, when I add water, in this case R, C, R dash, let me write it as it is, no difference, Cn, and this O minus which is there combines with H plus, and OH minus is given out, which we had taken at the start. So, these type of systems where there is Cn compound and OH compound attached to carbon, this we call it as cyanohydrins. Now, please remember once again that R and R dash does not necessarily mean only ketones here. It means that a setup of reaction possibly for aldehydes as well as ketones. But what is important is how do this reaction takes place, and what is the name of this final compound is cyanohydrins. So, that is what we are able to see here in the main mechanism, where the Cn minus nucleophile is attacking the carbonyl carbon, because Cn is minus and carbonyl carbon is electrophilic with the positive charge, and therefore, this type of final compounds we can name them as cyanohydrins. Intermediates mean that they are something which are formed in between, they are not stable as such, and those will only wait for some other reagent to attack. Here example is hydrogen ion, where it tends to form stable cyanohydrin compounds. Next one, reaction with sodium hydrogen sulphite. Henceforth, majority of the reactions will not be something new for you, it will almost be similar in cases where all these types of reactions will now involve the splitting of various types of compounds. So, suppose if I take a carbonyl group which is present here, and if I consider the sodium sulphite which is there. So, here also we know very well that splitting will be in Na plus and HSO3 minus. So, what should be the reaction here? HSO3 minus should attack the carbon, Na plus should attack the oxygen. So, that is what we are able to see here in the product, that this sort of a system will form where sodium ion will go with oxygen and this HSO3 minus will combine with the carbon which is there. So, in these cases we can get the final product by an hydrogen ion transfer, where in these parts the hydrogen is being transferred because alcoholic forms which are there will be very stable in nature, and therefore, you can see that the sodium atom which was earlier attached to oxygen is being transferred on other side for the sake of stability reasons. That process we call it as proton transfer. On the same basis, now reaction of these aldehydes and ketones with alcohols, where here what happens is two molecules or alcohols are utilized, because we see that there is a possibility where excess of alcohol, if it is present, can react to a particular system. So, what happens in these type of reactions is, suppose if we consider aldehydes, because these are reactive systems, we consider this as aldehydes, and if this is reacting with an alcohol in the presence of HCl gas, this is important. Now, in these parts, alcohol we know that it can either split as R plus OH minus, or it can split as RO minus H plus. Both these possibilities are there. So, this is only like acting like a base, this means that it is acting like an acid. But since you have already used an acid, the compound which is along with an acid will have to act as a base, because acid and acid will not react, acid and base will react. So, therefore, the splitting in this part, you can show it that this compound will rather split up as R plus, that is R dash plus and OH minus. So, who attacks where? Again the same theories here, where R, C, H and O, the pi bond of oxygen is broken. So, R plus has to now go and attack to the oxygen part. So, therefore, I can write it as R dash, because this is positive, this is electronegative, positive and negative. So, what should OH minus do now? It should come and attack to the carbon atom which is present. If excessive of alcohol is present, it is seen that if R dash OH, say another molecule in the presence of HCl gas if you take, then what happens is, because this hydrogen atom is pretty small, we are able to see that RCH as it is. I have not changed anything here. At the top also, let me keep it as it is, OR dash, because this is a large group, R dash is a large group. But at the bottom what happens is, the oxygen which is present will now be attached to R dash. So, we can see that the hydrogen here is replaced by R dash, and this hydrogen combines with this OH to form water as a byproduct. So, this is how we can see that we are able to form two types of compounds. This we call it as hemiacetal. Acetals here indicate the formations where OR is being present here, more like ethers, and this is called as acetal. Hemi because only half the reaction is done, and this is named as acetal because a complete reaction is done in this cases. So, this is how we can see the reaction where aldehydes are being converted into hemiacetals, followed by further reaction with alcohols can give us acetals. Moving on, reaction with bases. Now, what type of compounds tend to react with bases? Generally, from all our studies, say even from 9th standard, we have realized that bases would like to react with acids, and it will generally tend to form salts. But here the question is, are aldehydes and ketones acidic in nature? Acid indicates it should leave out H plus ion, but in the main functional group if you see, there is mainly C double bond O which is present. So, what sort of a reaction happens here is, let me take in the first place a pretty simple reaction which is present, where let me consider a simple aldehyde, and let me take ammonia as an example. Now, how is the splitting can be done is, in ammonia, this is the structure of ammonia. We know that there is a lone pair of electron, 3 hydrogen atoms which are there, and naturally between nitrogen and hydrogen, the electronegativity difference is bound to be there, that this is more electronegative, this is more electropositive. So, suppose if we induce a splitting here, what will happen? This can definitely split itself as NH2 minus plus H plus. The reason being, this is comparatively more electropositive. So, if you induce a splitting, naturally it will form H plus and NH2 minus. With this basic thing, again go back to your earlier concept itself, that whenever you do the reaction, this is electropositive, this is partially electronegative. So, if this is the splitting, now you know very well where who should go. So, what will happen here in this case? The down part, let me write it as it is, RCH as it is I have written. Then let me write with oxygen, one of the pi bonds are broken because that is a weak bond. and carbonyl carbon is positive, so the negative part of this should attack. So let me write it here as NH2, and the positive part is hydrogen that can go and attack to the oxygen. This is how I can form. So these are various amine types of compounds which is possible in these type of reactions. So this was a general reaction which was explained for a simple example of ammonia, but here now in the generalized reaction what they have considered is where the ammonia, one of the hydrogen is replaced by Z. Now what is this Z? Z basically is different types of groups which are directly attached to nitrogen atoms which are there. So these type of nitrogen atoms, when they are present, they are able to form an intermediate, and finally the removal of water takes place where they can form certain types of derivatives of these type of amines, which sometimes can also be named as imines, because if you remember in the Stephen reaction we had got imines as one of the intermediate compounds in the preparation. So this is how the various types of compounds can be generated, where suppose if we have different bases which are present. So with ammonia we can get imines, with other alkyl groups which are present, substituted alkyl groups, we get compounds which we call it as skiff bases. Hydroxylamines, hydrazine, various types of compounds are obtained. Now for example, in this case let me take up an example for our study, where let me take ketone, which is nothing but propanone, and other example let me take it as CH3NH2. This example which I am actually explaining is in the table. If you see the second part which is there for the second example, you are able to see the presence of the amine group where R is been replaced in those parts. So in all these cases here, the R group which you are able to see now, where in the amine parts the R here that I am going to consider is CH3 which is present. So what is the reaction that is happening now? Let me first undertake various type of splittings that are possible. CH3 plus, NH2 minus. This is quite natural, because whenever these type of splitting takes place, this is 1. If this is one type of splitting that is possible, there is another type of splitting also which is possible, NH minus H plus. The same compound, I have given two possibilities where it may either cut here or it may cut at N and H. Now which is better? Definitely this is better, because this is a small atom. So removing a small atom will be much easier than removing a big atom. So this type of splitting doesn't happen. It rather goes by this sort of splitting because of a smaller atom which is considered. So let us now undertake various attacks which are there. H plus should definitely attack the electronegative part, CH3, C, CH3, O, and H should come and attack here. Quite natural, because this is positive, this is negative. This negative part should now come and attack here, NHCH3, NHCH3 that I have attached to carbon. So this on further reaction we can get it as CH3, CCH3, and here in these parts which are there, OH and double bonded systems which are generally considered, where hydrogen can then give us CH3 compounds. So this is how various reactions are considered in these cases, where amines are able to give, along with the nitrogenous parts which are there, they can give various types of reactions which have been present here. So this is about the reaction of bases with amine systems which are under consideration, and the next part that we are going to see now is oxidation of aldehydes as well as ketones. What is oxidation? There are two aspects that we attribute. One is it may be addition of oxygen, the other is it may be removal of hydrogen. So in this case we are basically going to see about addition of oxygen compounds to this aldehydes. So very clearly you are able to see that if another oxygen is able to be added to aldehyde, it can tend to form carboxylic acids. Now in these cases you might either use strong oxidizing agents like potassium permanganate, potassium dichromate, or you can also use Tollon's reagent and Felling's reagent, because the aldehyde group which is there actually has on one side a small hydrogen atom. So because of this small hydrogen atom, even a weak oxidizing agent can help you donate another oxygen, and make it into carboxylic acid. But if you use a weak oxidizing agent to ketones, then it may not be possible, because for ketones you have big groups on both the sides. So, to introduce one oxygen in this case, you definitely need more stronger oxidizing agents in this case. So, what are the strong oxidizing agents that we have here? We see that this actually involves a breakage of carbon-carbon bond and followed by oxidation to those broken parts which are done. Now, when carbon-carbon bonds and all have to be broken, naturally it needs more energy and therefore higher temperatures are required in these cases. So, for example, how do this reaction tend to happen? That let us see. So, as a simple general example, let me take this as one of the ketones which is there, CH2 and R. Here I have just considered that CH2 group is an additional alkyl group which is present. To this, when I take oxidation, now the question here is, there could be a cleavage on this side or there could be a cleavage on this side. It can be on either side because this is the CO group. So, the question now is which side will be more flexible in these cases. So, because it is of a similar group, cleavage parts will naturally remain similar on either sides, but the only factor here is how do they oxidize. So, here we know that oxidation means it can involve removal of hydrogen as well as addition of oxygen. So, one of the product that you may get is RCOOH. How did we get that is RC and this carbon was oxidized. So, what do you mean by that? It has removed one hydrogen and then it has added another two oxygen. Where did you get oxygen from? It is been given from oxidizing agents. The equivalents are not denoted here, but what it basically means is oxygen is donated, hydrogen is taken away. So, what about the other product then? Plus it can also give RCH2COOH. Where did this come from? This side, RCH2CO, and here a minimum oxidation was offered where the OH group was introduced in these cases. So, this is how various type of oxidations can happen with ketones. So, there you are able to see multiple products where cleavage of C1-C2 bond or cleavage of C2-C3 bond. If you see the numbering of carbons in the figure there, it just says that it depends on which side of the bond you are cutting. Now, this is a problem with ketones, that you will be able to get a mixture of products, and the moment you have mixture of products, the problem then happens to be how do you separate these compounds. But then we do not have any other way for this. Whenever we do oxidation for ketones, we need high temperatures because they are flanked by large groups, and then after high temperature we get this type of mixed compounds as such. So, this is how various types of oxidation reactions are being done for aldehydes and ketones. There is another one special reaction that involves oxidation of methyl ketones. Now, this specific reaction is only restricted to the compounds which have methyl ketones, which means that CO group should have CH3 on one side and the other R can be anything. We know very well that generally for ketones we write it as RCOR dash, but very specifically in this type of system we should have such a thing. This is the speciality of this reaction, where methyl group is a must on one side of the carbonyl group. So, what they do is this tends to react with, say, sodium hypohalides. Now, halides here X, generally we do not use fluoride or iodide because of very high reactivity and very low reactivity. We prefer chlorine or bromine atoms in that X place. So, in these type of reactions what happens is, these methyl ketones which are there, they are able to oxidize themselves and form corresponding carboxylic acid salts. What do you mean by carboxylic acid salts? See, this is CH3COH, which is ethanoic acid. The same thing if I write it as CH3COONA, where the hydrogen which is acidic, I have replaced that hydrogen with Na. It means that it is a sodium salt of acetic acid or ethanoic acid. So, similar types of acids can be obtained here. So, what is the procedure here is that this tends to form RCOONA. Now, where did it get ONA from? RCO is here, ONA is coming from here. Now, what are left over? this actually tends to form CHX3. What is CHX3? CHCl3, very important compounds that we tend to come across, where halogenated compounds like chloroform and all we tend to come. So, this is one important byproduct that we tend to get here. So, if you see the balancing of the reaction in this case, now since you have to get CHX3, then naturally this will be 3 molecules of 3NaOX, and then we have to balance this part also, where we actually get 2 NaOH as the other byproduct. So, of the 3 NaO, 1 NaO has gone here, the other 2 are here. Of the 3 hydrogens, 1 hydrogen has gone with this byproduct, the other 2 hydrogens are here. So, this is how a special reaction with respect to ketones, and that too especially methyl ketones, is considered, where if reacted with the sodium hypochlorite salt which are there, we tend to get its corresponding salts of sodium, salts of acids. Along with that, the CHX3 type of compounds can be bromine or iodine compounds, and also another byproduct which is skipped because it is not a main byproduct of this reaction, the NaOH byproduct can be obtained in these cases. So, if these were all generally related to the aliphatic systems, we can also imply all of them into aromatic systems also. But now we have a very specific reaction of an aromatic system, which is electrophilic substitution reaction. All this time generally it was the nucleophile coming and attacking the carbonyl carbon, because carbonyl carbon was electron deficient, nucleophile was coming and attacking. Now, when we consider the electrophilic substitution reaction, we are going to take the simplest aldehyde which is present, which is benzaldehyde. Now, to this, if nitration is done, now what is nitration? We know that it is nothing but addition of HNO3 in the presence of H2SO4. This is something which we have studied many a times. And what is the electrophile generated here? It is NO2 plus. Generally, HNO3 we feel that it is ionized into H plus and NO3 minus, but in this case this will not be possible. Reason being, there is another strong acid which is present. So, if this is stronger acid, it will force this compound to act like a base, and that is why it has formed NO2 plus and OH minus. We know very well that OH indicates base. So, this is the electrophile which is generated in this part of the system. So, this is not going to be the substitution, this is the one which we do not require. So, this NO2 plus which is there should go and attack to this part now. Should it attack at ortho? Should it attack at meta? Should it attack at para? Where is the possibility? For this we need to know the resonance structures which are there, where once we try to write the resonance structures of aldehydes, this is electronegative, this is electropositive. If this is positive, it means it is electron deficient. Can an electron deficient donate electrons to benzene? Definitely not, because it itself is running short. So, what it does is, it rather takes electrons from the benzene ring. And we know that if these are electron withdrawing groups, the product that we get is meta products, that we have studied in the resonance parts which are there. If they are electron donating, we get ortho and para, and again in that para product is a major product. If it is an electron withdrawing group, then we tend to get meta products. This you must have studied in the first year parts concepts of resonance. So, what is the product that we can get here is the same benzaldehyde, and to that we can add at meta position, we can add NO2. Now, this HNO3, as told to you earlier, where NO2 plus will be the electrophile, OH minus is the other part which is split, and when you put a meta place, when you put NO2, you actually happen to remove an hydrogen here. So, that hydrogen will react with OH minus to form water as the byproduct. So, this is how various types of reactions tend to take place, where these type of electrophilic substitution reactions in this case will give you only meta products, because aldehydes, or for that matter even ketones, are electron withdrawing groups. So, this is about various reactions that can be encountered in the aldehydes and ketones part. And now let us see an assignment: which among aldehydes, ketones and carboxylic acids of similar masses have higher boiling points? Consider any example, you just got to say which has a higher boiling point among these three types, and you got to give a reason for it. Which among ethanol and hexanol is more soluble in water? Once again the attractions and all become important. Explain why aldehydes are generally more reactive than ketones in nucleophilic substitution reaction. It was very clearly explained to you, so you can explain about the steric factors and electronically important factors which are present with those parts. So now we have only studied certain basic reactions for this, and in the next segment now we will be studying the named reactions which are very important in this case of aldehydes and ketones. So till then, see you and hope you are back with the completed assignment for the next segment. Thank you. Sai Ram.